Very good afternoon, everyone. I hope you had a very good lunch, and now you're back to business again. So before we begin, don't worry. We're not going to ask you what did you have for lunch. Instead, we'll be presenting our session on breaking managed identity barriers in Azure services. So a little bit about myself. My name is Nitesh. I'm from Sikkim, a beautiful state in India. And we are actually really honored to be here at Black Hat Asia. This is our first time here at Black Hat Asia. So at Trend Micro, I work on the security and threat research, focusing on everything between code and cloud. So I've been presenting some of my work at conferences such as Black Hat USA, Hack in the Box, Hack in Paris, and a lot more. So we've been submitting vulnerabilities that have been found in cloud service providers, and particularly Microsoft, via the Zero-Day Initiative. I've been in the top 100 MSRC Most Valuable Researchers for 2023, and hopefully for 2024 even now. So you can find some of the fun stuff that I've worked on by going to my page. I also am on Twitter, or X. So yeah, so my findings range from vulnerabilities in home routers to Android apps, and now onto cloud services. Apart from my work, I'm mostly found playing bass and composing some vocals for my band. And yeah.
Hello, everyone. My name is David. I started my InfoSec journey back in 2010, starting as a malware analyst. Over the time, I gained some experience, presented on conferences such as AWAR and Caro. In the late 2017, I joined the Trend Micro and switched my focus more into the cloud threats and vulnerabilities. And I presented some of our team's initial findings in 2019 at the Security Fest. During the pandemic outbreak, I was one of the guys who was writing about the Team TNT activities and especially their switch to cloud focus and stealing cloud credentials. From time to time, I find also a vulnerability, and most importantly, I try to remain a human being.
So David found some issues in Azure Functions, the Azure Function Service in Microsoft Cloud. And I found some issues in Azure Machine Learning Service. And particularly, today we are going to talk about the issues in the Managed Identity implementation in Azure Functions and Azure Machine Learning Service.
But before we will tell you about our findings, let's tell you something about how we got there, because there's actually a funny story behind it. You know, in early 2022, the world was still recovering from the pandemic. And I was locked down in the Philippines in the hotel room. Although Philippines is a very sunny country, there was shade over the place. And without the vitamin D, it's just doesn't feel right. And there was one particular thing that made me happy that day. And that was when I found these issues inside the Azure functions. Then, a couple of months later, Nitesh was digging deep down into the Azure Machine Learning and found a lot of different issues. And after that, time passed. And in December last year, we met in Japan. And we were going from a party, sitting in a taxi, and it's, you know what, Nitesh? Let's apply for a Black Hat Asia. So here we are. So let me walk you through my journey inside the Azure functions. But first question I have to ask myself was, what are actually Azure functions, right? Well, I did what I usually do. I look up to the documentation and found out it's a serverless platform. But what is the serverless, right? It doesn't run somewhere in the skies. So we found out it's nothing more than running our user-provided code inside the cloud service provider on the managed platform.
Wait, David, did you just say running user code, that too on someone else's server, that too on cloud?
Well, I know what you're thinking, right? There is one saying among the developers, never trust user input. And now we are giving like executable code. What could go wrong, right? So don't worry, Nitesh. There are, some mechanism that prevents everyone from executing our code, such as authentication. And, we can harden user triggers that doesn't need to be a public endpoint that execute our Azure functions. So what we did, since we are providing a code into our cloud service, we did a simulation of compromise because we assumed that at one point in the time, the user will bring the vulnerability to the code. So basically, we designed our own serverless function, which was nothing more than a reverse shell that connected to our contrite environment. And from that, we analyzed the underlying environment powering the serverless or Azure functions, and also executed some commands, right? And observe the configuration changes, because not every feature inside the Azure function is available by default. So speaking of authentication, Azure functions get several options, starting with functions tokens. There are two scopes of the tokens. Functions token, which are basically binded to the function itself, and host token. With the host token, you can execute any function inside your serverless environment, and also it provides you the capability to execute some of the API of the function host. The second option, which is a little bit more secure, is using client certificate. And there is also a third option. Since we are actually providing the code for the executing the functions, we can implement a custom logic. And the client certificate is actually using the custom logic, but there are code snippets already available. Speaking of triggers, don't worry, it's not a landmine. The default one is HTTPS request. It's basically public endpoint. The second one are events that are binded to the cloud. And we can imagine like database trigger, just like that. One thing that we need to analyze as a researcher were the timeouts. How much time we do have inside the environment by default. It turns out that our reverse shell will be by default active for 5 minutes when our request will expire after 4.5 minutes due to the load balancer. And one important thing, you can limit your execution time inside the host.json file. Speaking of environment analysis, what do you do when you pop up a shell, right? Well, you ask, who am I? Turns out we are a root. Okay, that sounds nice, right? But, root isn't what it was before. So we need to execute another command, such as mount and cap shell. And we find out that by analyzing the output of this command, that we are running inside a container, Docker container, and our capabilities are limited, basically the default Docker capabilities. But there was one particular thing. We run this env command, which basically print out all of the environment variables. And there is the moment where it started to be interesting. But before I will speak about the environment issues, it's important to speak about the environment variables itself. Well, you might know it's very popular practice among the DevOps, and it often stores the secrets, right? And believe or not, there are some products that reference environment variable inside their documentation as a vault. And by all means, if they tell it's a vault, then I am telling that it's the same, like this was a prison for Pablo Escobar. So let's speak about the underlying fundamentals of environment variables. Well, you probably know that everything on Linux is a file, right? So we can just list the proc file system, and here's one file, environ, and we can print it out. That's basically the table of environment variables for the given process. And basically, we can access all of the environment variables of the running user inside our process namespace. And there is one very important thing. By default, the environment variables are inherited into every child process unless the explicitly new environment variable table are passed as arguments. We did a little demo for you. This is nothing more than simple hello world in C++, right? It doesn't even mention environment variables. So we export our super secret API key into environment variable, compile our application, run into the debugger, and break it at main function. And as you can see from the RDX is pointing on the stacks, just comparing the RSP RDX value. And if we follow the RDX, we can see it's also pointing on the stack. And there is something which notably similar to environment variable. And if we print out the address range, we can find all of the environmental variables, including our super secret API key.
But isn't this something like just specific to the debugger? Is it inherited by every process from the first PID itself?
That's a great question. We need to verify. So what we did, we actually analyzed it. Like first thought that it might be debugger, but unlikely, right? Because we got some knowledge. And then, okay, it can be, let's say, libc who is doing the job. But we found out that it's actually the kernel itself who pushes the environmental variables on the stack. So this function is called when a new process is spawned in the Linux. And one of the code snippets from the large function is this, where we can see actually how it's pushed into the stack. So back to the serverless functions. This is how the environmental variable printout looked like. It's a lot, isn't it? Hard to navigate. So we cut it a little bit for you. Still isn't it? But for our security purposes, this is the most important bits. So let's start with the Azure Web Job Storage. So what is this environment for? Well, it turns out that for Azure function, you need to store code somewhere. And in a lot of cases, you will need a storage account. And the storage account is used for storing the source code, and the Azure function host pull the source code, and then it executes it, right? And this Azure Web Job Storage is nothing more than connection string or access token to the storage account. So we can copy and paste to a cool tool called Azure Storage Explorer. And what we can find out here? Well, of course, the source code, some of the secrets, like function tokens, host tokens, and there's one thing. Unless we really harden it in the cloud, make the storage account not available to the public, or let's say disable the write access, what we can do, we can just delete and upload. But there is a bit, if we do the hardening, then if it's not publicly available, it's more tricky or inconvenient for the developer to put the source code there. And if we remove the write permission, then if you are just using the VS Code for pushing your source code of the serverless function, then it will not work, right? So what you can do, you can completely rewrite the function itself and execute your own code, and that's just by leaking your environmental variable. But next, and this is the most interesting and important environmental variable, is this container star context SI URL. It's short-lived URL, and if we follow the URL, we get something like this. It's basically the container configuration encrypted context. Well, looks nice, right? But what does it mean? Well, we did some digging, and it's basically the encrypted context is AES encrypted payload, where the first part is initialization vector, the second part is the payload itself, followed by the hash, and guess what was the decryption key? Anyone? Okay, I give you a hint. It's the container encryption key, the third environmental variable. So we can decrypt it, okay? Looks like that. But what we can get out of it? Well, of course, authentication tokens, but let's assume that we can execute the function anyway, so it doesn't add so much value, right? But most importantly, manage identity proxy settings. And we consider this should be hidden from the serverless environment itself. So we got Azure function. What are managed identity? We got Azure function, we got storage account, and we got a very nice image. And we want to work with this image inside our Azure function. And we don't want to put our credentials inside environmental variable. So what do? We use managed identities. This is how it looks like. The most important is it's running within the same container as the serverless function. This is how the reply looks like. So what is underneath? You got Azure functions, there is a binary running inside the same container. And because we decrypted the contents, we get all of the parameters for the proxy, including client certificate, endpoints, and some other parameters. And this is just forwarded from the binary to the public endpoint. This is forwarded back to get the token. So to sum up what we found, a lot of environmental variables, including proxy parameters. But what does it mean? Well, it turned out we can obtain a valid JWT tokens, and we can do it outside the Azure environment itself. And this is actually where it breaks the security barrier, because it should be hardening for inside the Azure. So just by leaking the environmental variables, we can obtain the tokens from the managed identities. But there's one important bit to mention. Of course, Azure is kind of secure platform, and unless you explicitly specify the permissions for the managed identities, you might get the token, but it got no permission at all. There's a little demo. So first of all, it simulates the leakage of the environmental variables, decrypted the encrypted context. As you can see here, this is the client certificate among other proxy parameters. Then we use it inside another, ask for the token. Once we get the token, we contact our storage account and get some metadata out of it. And this is all done outside the Azure. The only communication with the Azure environment was first communicating with the vulnerable function and getting leaked the environment variables itself. And there's one important question to answer. Why this all happens, right? Well, obviously, the important bit is the environment variable popularity itself. Sometimes when I am looking on these issues, I get the feeling that everyone feels it's safe, we use it, and we don't think what is underneath. And then there may be like slight code change, architecture change, some stress, and then it's just inherits to the say, child process. Or maybe, some might not know, maybe do know, but it's acceptable risk for us, and it's sometimes okay, right? But we as a security people should know about the consequences and telling others what could go wrong.
So that's a really strong statement of not knowing how to use an environment variable. What do you suggest, David?
Well, in this particular example, simplified architecture, we got the Azure function host, which is basically container image and a process which executes the language worker, which in our case was Python. And then you execute your user code. And because this container image is publicly accessible inside Microsoft Container Registry, we can play a little bit with it. And also use it inside our new serverless function. So what we did, we basically renamed our Python interpreter to Python int with a little hack and replace it with this compiled binary. And what this compiled binary, it utilized pseudo utility to run it on the different role-play user. And that's why, because, well, obviously, if we got code execution, which is the worst part, we could still read all of the environmental variables because we were running under same user because of the nature of the Unix, right? And then we pass a new environmental table, and here we can see only one environment variable. So we did our testing, and it turns out that for our serverless function, it's not needed at all. It was just needed for the function host, which actually spawns our serverless function. So it means it was just inherited. Maybe it was not even intentional. It just happened. We wrote some article about it back in then. Something about disclosure timeline. We originally find this issue in April 2022. We shared with Microsoft, but at the time of being, and with this cloud vulnerabilities or security issues, depends how you call it, there is sometimes blur line because we are assuming that the function is vulnerable by itself. So the severity, it's not that high. It's not traditional RCE. So we haven't been contacted back, so we released the blog post. A year later, NetSPI folks discovered the same issue. Credit for them, they were much more persistent, pushing the Microsoft to fix the issue. Now it's fixed. And generally, the binary was taken outside the container, And there was another container created. Then if you contact managed identity, it's running somewhere else, and the managed proxy is somewhere else. Although you can still get the credentials for the storage account from the environmental variables. Okay, this is our original blog post. This is the blog post of the NetSPI folks. And this is all for me. And now it's time for Nitesh. So Nitesh, stage is yours.
So thank you, David. I think the first episode was pretty good. Now we begin episode 2, that is on the Azure Machine Learning service. So these days, AI is being sprinkled in almost everything that we are going to use or going to be, get going eventually. And it's super cool. By now, we have somewhere or the other been, exposed to these services, or at least, tried your hands on or something. So these are all the services that are based on the Azure AI platform, and it depends on the Azure AI offerings. So the applied AI services are the offerings which basically solve a business problem. These are followed by the cognitive services that are the machine learning models that are offered as a service, which is consumed by the applied AI service and eventually the applications that we use. And all of this is actually built on top of Azure Machine Learning service. So, well, Azure Machine Learning is a cloud-based machine learning as a service offering from Microsoft. In AML, you create a workspace, and this workspace is basically the centralized place to do your machine learning operations. So ML ops eventually falls down to having some compute, having some cloud storage, and a way to monitor the logs, and there are a few more other parameters to it. So the workspace is dependent on certain Azure services like the storage account, the Azure Key Vault, the Azure Container Registry, and the Application Insight services. So the storage account, for each workspace, a storage account is created, where the storage account is used to keep your machine learning models and your machine learning data sets as well, like data sets, Jupyter notebooks, logs, models, snapshots, Python scripts, and all of these other things. This is where you keep your stuff. And there are various other compute options that Azure ML provides where you can run your code. And compute instances are managed Ubuntu virtual machines. By managed, we mean that the security of the host OS, everything is managed by Microsoft themselves. So the OS image contains like various tools used by developers such as Jupyter, Jupyter Notebooks, VS Code, Conda, Docker, Python, and all of these other things. Unlike Azure Functions, we have complete root access to this virtual machine or the compute instance. Additionally, these compute instances contain certain programs or middleware agents that are created and maintained by the cloud service provider, in this case, Microsoft. So these are like secret, undocumented agents that are used to configure environments, diagnose environments, and do a lot of other stuff. And sometimes open up avenues of information disclosure and code execution as well. So these may be open source, like OMI, or these may be closed source, as we'll see in a bit. So the compute instance is where you run your code, and the storage account is where you keep your stuff. Okay? So the approach was not very magical. Since we had root access to the compute instance, we wanted to inspect the network traffic that is going in and out when we do something. We want to check the running processes to find such agents. Reverse those cloud service provided agents because they're not open source, and maybe we can find some undocumented API or some overly permissive API. And of course, explore the logs that are generated when we do something. So as David shared earlier, this is a similar example. Let's say we have a function app and a compute instance in a user's subscription. And we want these Azure resources to access a storage account. So one of the ways is to hardcode credentials, but that's not a recommended way. We have a CWE for it. And Microsoft recommends using something that is called a managed identity. So the first type of managed identities is a user-assigned managed identity. So this identity can span across resources and can be also used by multiple resources. For instance, in this case, we can use one single user-assigned managed identity to allow the function app and the compute instance to access the storage account. The second type of managed identities are system-assigned managed identities. This identity is specific and tied to the life cycle of the resource to which you assign it. And these identities cannot span across resources. To get going with managed identities using Azure CLI, you can run az login followed by this flag of -- identity. Since we have root access to the virtual machine or the compute instance, what happens when we run this command? A GET request is sent to a local port, which is 46808. And again, since we have root access, we are able to figure out which is the underlying process that is listening on this port. In this case, it is identity responder D. Well, what is identity responder D? It is a powerful daemon. It runs as root. And it is also known as Azure Batch AI Identity Responder daemon. So does it respond with some identities, some tokens? We'll see in a bit. And it also fetches its configurations that are stored as environment variables in files. So these are the locations of the files. So these are some of the environment variables that are used by Identity Responder daemon to get going with a compute instance. And particularly, MSI endpoint, MSI secret, and the cert URL, these are the three important environment variables that we need to focus on. Well, we just want to figure out how does the outbound traffic look like to see whether we can do something about it. So we have eventually this post request where the host header is set, and the post request body contains the certificate thumbprint and the compute instance name that is set as the instance ID, and the resource for which we are getting the token for. And to talk to this endpoint, we need a pair of certificate and a private key from this hard-coded port path on all compute instances that you will ever create. So overall, we have this compute instance, which contains a binary, that is identity responder daemon. Remember that this is a closed source binary. We don't have any public code available for this, which talks to a public endpoint using a pair of certificate and a private key. And in the response, the managed identity JWTs can be fetched and used from the compute instance. Let's say the certificate and the key pair are compromised in an assumed breach scenario, like a post-compromise scenario. These are compromised and exfiltrated from the compute instance. Could an attacker still use the same pair of certificate and key pair to get the managed identity token from non-Azure environments? Let's try to bypass the security boundary right now. We found that we could not. So we got a 401 unauthorized. So we're like, OK, so did Microsoft really win there? Let's see. So the certificate and the key pair, they are actually tied to the compute instance. And these are unique per compute instances. So like no two pairs of certificate and a private key will ever be equal. But was that it? Like we could have just packed our bags and left. But no, just kidding. So enter DSi Mount agent. DSi Mount agent is another binary that exists on all compute instances, which again runs as root. It is known as batch AI DSi Mount agent. And it also fetches its configuration from environment variables stored in files, like the same environment variables, David. So yeah. So this is the same binary same agent that we found vulnerability in last year for Black Hat USA. So we found a bug in the binary itself, wherein a network adjacent attacker could basically fetch logs for any service. And in this case, you can see we can fetch these logs for Jupyter service because Jupyter is installed on all compute instances. So let's say if you are a data scientist who is using compute instances and running some commands as sudo using the Jupyter terminal, they would get in the logs. And these logs can be viewed by a network adjacent attacker. And this issue was later fixed with this CVE. Now I'd like to present what was initially planned for last year's Black Hat USA, but things changed the last minute. So the configuration files for DSi Mount agent contain certain interesting environment variables, like some symmetric key, some certificate, cluster certificate, some cluster private key, some XDS endpoint. So what is happening here? Well, the purpose of DSi Mount agent is to make sure that the file share of the storage account for this workspace is mounted on the compute instance. And it does so by checking every 2 minutes. So its job is just to make sure that the file share is mounted on the compute instance. So it turns out the DSi Mount agent talks to the batch AI XDS endpoint using the same pair of certificate and the private key that identity responder daemon uses. And in the response, we get something. What do we get? So eventually, the post request, like the outbound traffic, looks something like this. So we are not concerned about the post request or the headers and all. We'll just focus on the request body, because from here onwards, the certificates are the same, the endpoint is the same, the URI is the same. So yeah, let's see what is the response for request type get workspace. So we reversed the binary, DSi Mount agent, and we found this function called clients get workspace info in this binary, and we have this request type set to get workspace, which is the post request body. This request is sent to the batch A XDS endpoint using the same pair of certificate and the private key that we saw earlier. And in the response, we get the AML workspace's metadata. This metadata contains information such as the storage accounts, resource ID, the key vaults, application insights, the tenant IDs, the subscription ID. So this can be thought of like the who am I of the AML workspace. Later, we come across another request which looks like this. So we have a function called get workspace secrets, where the request type is set to get workspace secrets. Just note that this binary is not open source, so we are able to find this after we have reversed the binary. And in the response, we get an encrypted form of the storage account's access key. So the response is decrypted by certain environment variables that are, again, stored in files for the DSi Mount agent and the DSi idle stop agent, which is a different binary. So using these two environment variables, we get the decrypted symmetric key. And using this decrypted symmetric key, we are able to decrypt the response that we saw and eventually obtain the storage account's access key. And that's where David helped me. So,
You're welcome.
thank you. So the attack scenario is something like this. We have a certificate and a private key and a bunch of environment variables that are stored in files. These variables are used as configurations for these middleware agents. And you can use these to get the storage account's access key. Let's say these three files are compromised. Now, what would you do to invalidate the storage account's access key?
Well, Nitesh, what about if we rotate the keys, right?
That's a good idea. Let's see whether that works. So on the left, I have the AML workspace, and on the right, I have a bash terminal open on my laptop. So on the AML workspace, I navigate to the storage account, and I go to the access keys section. Now, we view the primary access key, and we copy this to the terminal on the, okay, let me just play this again. So yeah, on the left, we have the AML workspace, and we go to the storage account. So after we go to the storage account, we go to the access keys. And we copy the first, like the primary access key that is being used with this storage account. So after we have copied this, we will run the POC where I have exfiltrated the certificate and the private key, so we are able to get the current storage account's access key. Now, what we will do is, we will generate the storage account's access key again. We'll basically rotate the key. So now that the key has been rotated, we will copy this newly generated key back to our terminal. And now we will synchronize the AML workspace to use this new storage account's access key. So once this synchronization has completed, we will go back to our terminal, and we will rerun the POC to see whether we can get the rotated storage account's access key. And as you can see, we got the rotated storage account's access key as well. Does the story end here? Like all the stories that could have been? This one does not really end so fast. So there were a few more agents that talked to such public endpoints using a pair of certificate and a private key. And in the response, we get certain crown jewels like storage accounts access key, the AML workspace, metadata information, and a lot of other things. There were a few more agents that we could look into and reverse and figure out what else can we fetch using the storage accounts access key, using the certificates and the private keys, basically. So the idea was to find what else can we request and what else can be the parameters for request type in the post request body. So the function, for example, get workspace secrets calls another function that is generate XDS API request schema. So the post request's body is generated by this function. So the request type parameter is populated by this function. So the idea was to look at all the cross references across all the binaries to this particular function and find out what else could be done. And this is the list that we came up with. In this, we have generate SAS, generate data store credentials, get ACR token, get secret. So we pick get AAD token because that's interesting. And then back then, I don't think Azure was renamed to Entra, so we were good. So this function called get AAD token, which is there in the host tools package for identity responder daemon, host tools, and a lot of other binaries as well. So this is how the request body looks like, where we have the request type set to get AAD token, and the request body contains the resource for which we are fetching the token for. This is sent to the same batch AIXDS endpoint, and in the response, we get the Entra ID JWT of the managed identity that was assigned. This is how the response looked like. And similarly, for fetching the user-assigned managed identity, we just specify the client ID in the request, and we get the Entra ID JWT of the user-assigned managed identity. Quick recap. So we have certain binaries in compute instances that talk to public endpoints using a pair of certificate and a private key. And we can fetch so this is how the compute instance fetches the whoami of the ML workspace, the storage accounts key, the JWTs for the managed identities, and a lot more other stuff. And if these credentials are compromised in a post-compromise scenario, an attacker could do the same.
Wow. But we can use the logs, right? We can see the activity that something happened.
OK, you leverage the logs. Let's find out. Well, let's do some legitimate activity. This is using the Azure ML SDK, or you could just run az login -- identity from the compute instance. And using the certificate and the key pair from the same compute instance outside the compute instance, let's say this is already compromised, we run this request, and we get these logs. So the difference between the attacker logs and the compute instance logs don't really signify something important that we can bank on to figure out whether this request came in from the compute instance or from an attacker's environment. And as you can see, the sign-in details don't contain any information about the IP address. So that would have been one indicator that you could have banked on, but you can't.
So how do we detect that someone has stolen our certificates?
You can't use the logs, David.
That's so
too bad.
Yeah, well, but let me rephrase. Why is this even a vulnerability? Can you explain about that?
OK. So when we go to the documentation for Microsoft, we came across this one particular mention about identities, managed identities, is that by design, only the Azure resource to which we have assigned the identity can use this identity to request tokens from Azure AD. But we are able to use the certificates and the private keys to fetch tokens outside the resource to which the identity has been assigned.
So trust, but did you verify? The documentation could be outdated. We all know who develops software. We don't like doing documentation.
OK. Well, everyone someday, somewhere needs someone whom they can absolutely trust and believe in. To confirm things from the logs themselves, we dialed in Azure support. So we called Azure support, and I asked them, why don't the managed identity sign-in logs contain any IP address? And this is what they came back with. So the assumption is that the managed identity tokens are fetched from a local endpoint, so just like AWS IMDS endpoint. So in this case, because of the feature of managed identities, the logs are not helpful that you can bank on. Later, just to be sure about things, it turns out that the certificate couldn't be figured out whether it came from, where the request actually came from. And again, they said, OK, Microsoft Entra does not record the IP address because it is assumed that the sign-in happened from the targeted managed identity resource. So like a quick note on the persistence. So using the certificate and the private key, you can get the rotated keys, the JWTs for managed identities. The certificate is valid for 2 full years. So if you have a compromise, you wouldn't know for at least 2 years that somebody else had the backdoor access. And yeah, to invalidate the certificate, you need to delete the compute instance. And obviously, these logging discrepancies can be really helpful for attackers. So the disclosure timeline looks interesting for this. So we had planned to share this research with the community back in Black Hat USA. However, the vulnerability was reproducible and not fixed before the talk was recorded. We reached out to Microsoft, and they deemed the bug to be of a low severity And later, upon Microsoft's request, we redacted the details, although this bug was over the 90-day ZDI disclosure policy, and it was reproducible as well. Microsoft has recently confirmed that the vulnerability has been patched, and we have also validated on our end. Currently, the fix does not allow the certificate and the key pair to be used outside compute instances. Later, we'll be releasing this blog by 22nd of April, so stay tuned on that as well.
So how many services support managed identities anyway?
Yeah, that's cool. There are over 50 plus Azure services that can support Azure Managed Identities. So we have looked into Azure App Services, Azure Machine Learning Service. So possibly, researchers, you can look into other services to find more variants and find logging discrepancies in the service. All right, time to wake up, folks. So back to the takeaways.
Yeah, so if you sleep till night, there's key takeaways to take from this talk. I'm not saying you can't use environmental variable, inject secret inside this, but you have to be very careful when you do it and know the consequences, and that the things can get very bad, and it's definitely not a vault. Well, it's always good to threat model cloud service provider services to get an idea what could get wrong, and perhaps create an action plan if something gets wrong. Because, if you hardcode secrets and then you find a leak and you have to rotate at it, it's pain. Yeah. But if you store them in the vault, you can do it by one click. Also, one of the security cliché, follow principle of least privilege, and this is especially important for the cloud deployments, because single access token could lead to the full cloud account compromise, especially if you get like high privilege or like service principle. If you are a threat researcher, examine cloud APIs, find the bugs, and make the whole environment even more secure.
So it's very important to test and secure your authentication and authorization scopes. So from where you can use these certificate-based like authentication to work. Definitely, if we had the actionable logging, then we could have detected such sort of things, and you could have been much more secure. Such assumed breach approach can lead to such security findings as well, and that would be really hard to detect. And obviously, challenge official documentation, and don't forget to call Azure support. We'd like to acknowledge Zero Day Initiative for helping us out with getting the bugs across Microsoft. And now we open the floor for any questions that you may have. I think we have one question. OK.
I'm Paul, your colleague. So do you have a recommendation for those stolen certificates? I mean, how the SOC can detect it?
So based on the logs that we found, the SOC could not be able to detect whether the certificate abuse was happening from an Azure environment or from an attacker's environment. Because one of the factors that one would bank on would be an IP address, but the IP address is not there in the signed-in logs.
Not also recorded. Okay.
You would have to detect the initial break-in, but you wouldn't detect that something was leaked, perhaps. Or used to leak, maybe, but used not.
OK.
All right. Thank you.
If you have any other questions, we'll be down in the hallway, and we'll be also back here tomorrow, so we can connect there. These are our QR codes. Feel free to reach out. And thank you for attending Breaking Managed Identity Barriers in Azure Services once again. We are David and Nitesh, and we'll be back with some cool stuff. Thank you.